So when you read these problems, what I usually do is I start with what type of data would I get from this? So if we're looking at problem number 1, what type of data am I going to be collecting? Time, right? How would you do time? Does time have labels? Yeah. The reason why I'm pointing that out is if you're measuring something that has labels, is that going to be qualitative or quantitative? Quantitative. Whenever you're talking about quantitative data, it's going to be a t-test. Okay? Understand? And you're going to be finding means. So I know, looking at number 1, that I'm going to be using t's. It says which takes less time to travel. So I can either do a confidence interval or a hypothesis test. Is this going to be a 1 sample or a 2 sample? Do I have 1 set of data? Do I have 2 set of data? I have 2 because I have car and train. Is this going to be paired or not paired? Paired. Why is it paired? Paired by individual. So this is going to be a paired t-test. You can call it a 2-sample paired, or you can just call it a mean of differences. And I'm putting that down there for you, that mean of differences, so that you know when you're talking about it. It's the mean of differences because you took the differences first. Then you did 1 average. So for number 2, she checks the cement bonds, who do not. This one I can really argue in either direction, because what would you think the data would look like with this? Proportion? Kind of like each person would be yes or no? Okay. If you were doing proportion, what kind of a test would you do? 2-sample z-test. If you did a test, would you pool or not pool? One of them you pool, one of them you don't. A hypothesis test is always going to be centered around what main idea? The hypothesis. And the hypothesis is that there is no difference. So would you pool or not pool? You would pool. You don't pool with the confidence interval because the confidence interval is based off of whatever you saw in your sample. Okay, so the only time you pool in this class, only time, is going to be in a 2-proportion z-test. Nothing else is pooled. All right, and that's if we're saying if it is loose or not. If you were going to be talking about like a level of strength, like it is attached, I don't know, it can withstand so much pressure. If you wanted to do this a different way, you could make the argument on this that is a t-test. I don't know how bonds are measured. So I would have said, oh, there's about I would have looked at it and said this student or this child's braces are 90% attached. And then another's braces might be 75%. Because I've got these different numbers and it's not just yes or no, I would have done a t-test. All right, looking at number 3. What kind of data do we have on number 3? Averages of time, right? T's or Z's? T's, 1 sample, 2 sample. 1, okay. Further to discomfort sedated. Yep, because we're not looking at what they did with and without the antihistamine. Everybody's taking it, so it's just a 1 sample. Test or confidence interval? Confidence interval. So this is going to be a 1 sample T interval. Do you guys have questions on what we're going through with this? This to me, this is where it's like make or break. Because if you can't answer this question correctly, then none of the work you do with it is going to be right. All right, what about number 4? Yeah. 2, okay, so we've got 2 samples because we have, it's really nice, they tell us 472 men versus 552 women, so we know that we've got 2 samples. Are we going to be dealing with Z's or T's? Z's. Why Z's? It's a rate. 6% of. I'm going to have successes and failures. So this is going to be a 2-sample Z test because it says does this. Okay? How are you doing with that? All right. Go ahead and read these 2 situations for me. Honestly, the question was, is this the way the free responses are going to be formatted? This is generally, there's usually at least like one free response that it's just a question. But sometimes they will still prompt you on things afterwards. But you're going to be given an information set, and you will have to decide. They're never going to tell you, do a 2-sample Z interval. Okay? They're going to just ask you, does it, or how much of, or what would you expect? Yes or no questions are tests. How much or what should you expect questions are intervals. This here, though, what's different about this? Does this match what we've been talking about? No, what kind of data do I have here? We have categorical, but it's not a success or failure, right? It's not an either you passed or you failed. It's categorical, but I have accident, illegal activities, illness, or other. So this is different. Same thing with this one. We have this idea of categories. And you can compare one group across categories. You can compare multiple groups across categories. But you can't do it with a T or with a Z. Okay? These guys is what we're working on for this little chapter / unit. Okay? It's only in chapter 25. And what we're talking about here is counted data. And that means it's kind of like proportions, but instead of just proportion male, proportion female, instead of just proportion people with blue eyes or non-blue eyes. Now we're going to extend that and talk about blue eyes, brown eyes, green eyes, weird eyes. I would be in there, multiple colors. Yay. Those of us with different colored eyes. Yeah, I took my brother until I was in my 20s before he noticed that. All right, so these are counted data. Who in here are my AP Bio folks? Have taken it or are taking it? What do I do with this? Chi-squared. Yes. Hey, but I've got very great news for you guys. For all of my AP Bio folks who did this all by hand. Oh, heck no. We're still going to be writing a little bit of this, but we don't have to do every single calculation by hand. In statistics, we work smarter, not harder. Okay? We try to get something else to do as much of the test as humanly possible. But chapter 25 is about comparing counts. It's still this idea of inference. But part of the reason why this unit, or the AP College Board views this as one unit, it's a teeny tiny little unit. And it's teeny tiny because we don't do intervals for this. We don't. We don't do intervals for this at all. It is all just tests, and they're very similar. When I show you one test, you're going to see that the computations for all the other tests are going to work exactly the same. They just have different names. Okay? So, what the heck is a chi-squared model? And by the way, CHI, when you are in this class, that is chi. That's not chi. That's not chia. That is not chai. Does chai even spell? Chai has an A in it, right? See, it's not even chai. So do not tell me it's a chi-square test. Do you understand? Okay. No, I don't get it. We are going to be starting first with something called a goodness of fit test. And that's kind of like looking at know, looking at M&Ms. When we're talking about M&Ms, they'll say that I think 20% are blue, 13% are yellow. They'll give you multiple percentages, and you're trying to see goodness of fit. How good does your data fit the model? And for a goodness of fit test, we are going to have degrees of freedom here. The degrees of freedom is n minus 1, where n is the number of categories. So it's like if I were to talk about M&Ms, n would be the number of colors. Okay? Now, the chi-squared test, all of them, are only used for testing hypotheses. They will not be used for confidence intervals at all. Yay, there goes half of our work. Right? It's not, hey, do a hypothesis. Now turn around and do a confidence interval. You don't have this with this. Your chi-squared tests are always one-sided tests. Okay? Chi-squared is always going to be one-sided. And with that, when we write our chi-squared null and alternative hypothesis, we really just do it in words. We say something along the lines of the distribution of M&M colors, or M&Ms by color, matches Mars's claimed distribution. And the alternative would just be, it does not. Okay? So we're only doing a hypothesis test. That hypothesis test only has one side. And because it only has one side, when we're talking about how I'm going to reject something, we're not going to say that it's more than, we're not going to say that it's less than, we're just going to say that it doesn't fit. It's kind of like sticking to a not equal to, but it's only one-sided direction. And I don't think I've got it pictured in here, but when we're talking about a chi-squared model, the distribution for a chi-squared model, depending upon how many degrees of freedom you have, it's a very heavily skewed model, and it basically kind of will go like that. And when we find our chi-squared statistic, with however many degrees of freedom that it is, our p-value is always going to be the area to the right. Always. Okay? And the steepness of that hump and the thickness of the tail, all of that will change depending upon your degrees of freedom, but it's not normal. That's a really big thing that I need you to see here. Chi-squared is not normal, doesn't even come close to it. So because it's not normal, we are not going to have a mean. We are not going to have a standard deviation. We will have degrees of freedom. Okay? We will have a chi-squared statistic, but it is not normal. It is not symmetric, and that plays a huge role in what we're talking about here. So because we're non-normal, because the first thing that we do when we're trying to figure out anything is decide what kind of data we have, we do that for our assumptions and conditions. So when we were talking about proportions, my big thing is it had to have been success-failure. When we were talking about means, we had to have some type of number that I could do averages with. Counted data is what we need for a chi-squared distribution. Data's got to be counts. And when we talk about counts, counts are always going to be whole numbers. So all you're going to see, or all you really should see, are whole numbers on a table. Remember way back in the beginning when we were doing problems that had to deal with like the Titanic and survival rates based off of class? That's counted data. You count how many people fit into these categories. That's the very first thing. Then we go into the independence assumption. And one of the things that chi-squared actually answers for us, one of our chi-squared tests, is a test for independence. So this is kind of a harder assumption to nail down because one of the things we are actually measuring is going to be independence. But what we need to be able to say is that each thing in each of my cells, so each of my people that are represented by the cells, each of the M&Ms that I'm counting, each of those have to be independent of each other. We're not talking about is class independent of survival rate? Are those two independent factors? We're not talking about that. We're talking about each specific element within the cell. And to try to help us reach that, we have the randomization condition. We've got to randomly select it. Now, just so that you know, when we do experiments, the randomization condition is very, very hard to deal with, and that's because typically with experiments, you're dealing with the individual volunteers or the people that you can get. But we include a little bit of randomization when we're applying them to treatments. Now, this is the big one. For chi-squared, the biggest two issues, you need counted data, and you have and that means your expected counts. What should you expect to see? Now, please understand that is expected. Remember when we were dealing with proportions and we were saying success failures? 10? When we were doing tests, that was the expected count. You used your null proportion to find that. This is expected count. You're going to use the proportions that you expect. So if Mars says that 20% of M&Ms are going to be blue, then when I calculate 20% of my sample size, that number has to be at least 5. Eden, are you okay? All right. Expected cell count has to be at least 5. For my AP Bios, did you guys do assumptions and conditions for chi-squared? No? Didn't talk about it? Okay. So we're fluffing that up a little bit more. For those of you who didn't take AP Bio, don't worry. You're great. We're going over the whole thing anyway. Questions so far? So the big things here that are different from our other tests, chi-squared, we want data to be counts, and our expected cells have to be bigger than 5. All right. So how do we calculate chi-squared? Basically what we do, the very first thing, is we find the expected value. And what we're talking about right now is we're starting with kind of the easiest. There are actually 3 chi-squared tests. There's goodness of fit, there's independence, and everyone's favorite word, homogeneity. So we have three different types of tests for chi-squared. They all work out very, very similarly. The big difference is when we're talking about expected cells. If you are doing goodness of fit, which is what we're starting with, then all you're going to do is you're going to take the total of your sample size and you're going to times your expected proportions by that total. So if I think I should have 20% blue and I'm doing 100 M&Ms, I would expect 20 M&Ms that are blue. If I was only going to take 25 M&Ms, I would multiply 0.2 times 25. That's how you get your expected cell count. Very, very simple. It's the product of the total number of observations times whatever proportion you expect to see for that count or for that category. Then we're going to be calculating what are called residuals. Let's see here. How do I say this? I had to clean my shower this weekend. I had to scrub the residue off the glass. Residue made by soap. What is residue? Leftovers. Like what's stuck behind? Well, when we're talking about residuals here, we're talking about what is the difference between what I expected to see and what I actually saw. And so if you think about it, when we're talking about test statistics, we said that Z was observed minus expected divided by standard deviation. That top part is the residual. That is the reserved minus the expected. Then you're going to square those residuals. So do observed minus expected squared. And then for each component, for each cell, we're going to do this calculation. So we did observed minus expected, we squared it, and we come back and divide it by whatever was expected. This sounds like a pain in the tuchus. And if you were in AP Bio and you had to do that by hand for every single cell, it is a pain in the tuchus. We're going to be doing this with your calculator, bless you. So I will be giving you simpler, or not really simpler steps, but all of this is done by typing in list 1, list 2. Okay? Very straightforward, very nice, very clean. Okay, still see people writing. You good with that? Okay. So it's not quite done yet. Once you have found each of your components, you take all of your components and add them together. That's actually what your chi-squared statistic is. So like when we were talking about our t statistic or our z statistic, we did just observed minus expected divided by standard deviation. Our chi-squared component is the sum of all of my observed minus expected squares divided by the expected. Again, your calculator will do this for you. It's pretty freaking nice. Okay, we're going to do the degrees of freedom. And when we're talking about goodness of fit, it's nice and simple because you only have one row or one column. It's just the number of cells minus 1. It's just the n minus 1. And then we'll use our chi-squared test statistic to find the p-value. So if we go back to this graph, we have my chi-squared distribution. You're going to find your chi-squared test statistic. And then to find this p-value, it is always going to be the probability of being greater than whatever that chi-squared number was. Always. You don't have to worry about less than, greater than, equal to. It's always going to be greater than. And basically what you're going to see is the larger your chi-squared value is, and these guys get big. Like, it's not, if you have a chi-squared test statistic that's like 2 or 3, I guarantee you're pretty much going to fail to reject. Because you got lots of area. You're going to have much bigger numbers. You'll have like 14, 24, 38. You're going to get much bigger numbers. And a large chi-squared value says that we're pretty darn far from what I was expecting. There are no negative chi-squares. That's why I drew this line here, because chi-square doesn't go to the negatives. When we're talking about normal distribution, we have positive and negative z-scores or t-scores. You don't have that with this. All right. Read the problem. All right, this isn't an appropriate question at all, is it? Coronavirus, germiest, grossest, nastiest, which bathrooms use the most? I promise you, unfortunately, especially my ladies, this will change the way you go to the bathroom the rest of your life. Yay! And this is actually, have any of you ever watched Mythbusters before? You have? It's really kind of a cool show. It's hilarious. This is an actual episode. If we had time, I'd say, hey, let's watch the episode. But we can go through and we can do this by ourselves. It says, we want to ascertain if there is evidence to support the myth. We're going to test the hypothesis. The stalls are selected randomly. So, what we're going to do is we are going to set up our table. We're going to write the null and alternative hypothesis. We're going to verify our conditions, show mechanics, and find the p-value. We are going to go through all of our steps with this problem. Okay, start to finish. Here we go. So I'm going to start looking at this problem and saying, what question are we trying to answer? That's usually the best thing. Start with what question are you trying to get to? What do you think? Do you see anything that might give it away in the question? So we have a theory that the bathroom stall closest to the entrance is least used and therefore contains the least amount of bacteria. Do you understand what I'm talking about? So we're talking about what? The stall is the dirtiest. Am I measuring which stall is the dirtiest? Am I measuring bacteria counts? What is my data? How many people use it? So what we're looking at is we've got people that are going to be recording the stall number that they used. So when we do all of our general hypothesis tests, especially when we're looking for differences, our null hypothesis is usually that there is no difference, right? Where the alternative is that there is some kind of a difference. For the goodness of fit model, our null hypothesis is going to be that there is no difference. And so I'm going to say there is no difference in the number of people who use each stall in a public restroom. It's not a fun hypothesis to write because there are a lot of words. But you want to see how nice the alternative is? Watch the alternative. I say there is a difference. And then just drop the quote marks. And that is perfectly appropriate. Because basically what I'm doing is I'm telling you that I'm changing no difference to is a difference. Everything else stays the same. Okay? Now, for my assumptions and conditions, and I'm actually going to, let's take my assumptions and conditions down here a little bit. What are my assumptions and conditions for a chi-squared test? Counted data. So data are counts of what? What are we counting? People. Counts of people. Bless you. What else do I need for a chi-squared test? Randomization. Do we have randomization? I mean, I didn't pick the people randomly. I didn't assign them to anything randomly. So if we don't have random, what do we need? Hope representative. So we're going to hope sample is representative. Okay. What else do I need for chi-squared? What was that last condition? Sample size. So in order to do the sample size, I actually have to kind of start filling out my table. Now the way that I fill out my table is I always start with observed. So if I look at my observed, let's see here. We have 1, 2, 3, 4. Those are my stalls. How many people did I see go into the first stall? 23. Then we had 38. Then we had, and lastly, 24. And so just to kind of keep an idea here, how many total is that? They kind of told you also. 119. Now, our null hypothesis is that there is no difference in the number of people who use each stall. If there is no difference, how can I figure out what I would expect? And it really doesn't have as much to do with this as it has to deal with this. If there's no difference in stall usage, what should you expect? How many would you expect to be in the first stall? Divided by 4. So what is 119 divided by 4? 9.75? 29. I was going to say, that's a little small. 29.75. And hey, you know what's great? If my expected thing is that there is no difference, that means all of these. Are 29.75. So this, I took the total and I divided it by 4 to get my expected count. So going back to our assumptions and conditions, what is my last assumption or condition for counted data? What did we say had to be true? Everything's 5. And for that, we're looking at this column. And by the way, your expected data can be decimals. Your observed data cannot. It's perfectly fine for this to be decimals. And so we will say all expected counts are going to be greater than 5. I think it's really greater than or equal to. Now, ladies and gentlemen, you have a choice. You can either write down all of your expected counts. In this case, it's easy. All expected counts, 29.75, are greater than 5. Or what I recommend doing is I do the table. And you'll see as we go through there that sometimes it just might mean writing a little number. But you have to actually show your expected counts. If you don't show it, it didn't happen. Okay? So we've done our assumptions and conditions. We've done our hypothesis. We've found the expected counts. What do we do next? Find the residuals. How do I find a residual? Observed minus expected. Okay? So I need you to tell me. I'm not going to do math here. Well, I might. I am the math teacher afterwards. After all, maybe I should do the math. I'm not going to do any math. I refuse. Rebel without a cause. Okay. Give me another color pencil. I like my colors. Grün. Okay, here we go. So I want you guys to calculate your residuals. Okay, so what is my residual for the first stall? Negative 0.75 for the second stall. 8. It's not 8.75, 8.25. For stall 3. 4.25, and for stall 4, negative 5.75. Okay? What do you think all my residuals will add up to? 0, right? Because if I'm over on some and under on the others, all in all these guys in both cases are going to add up to the same thing. They're going to add up to 119. So I calculate my residuals. Then what do? Square them, our residuals. So we've computed the residuals. I'm going to square my residuals. And I'm coming up with, and by the way, what I'm doing, because I'm lazy, I put observed, I put expected. Then I did observed minus expected. Then I did that guy squared. And we will make this go a little bit quicker also. So that means my residuals here are going to be 45.563, 68.063, 18.063, and 33.063. What that's going to do is that makes it so that my residuals, I'm only looking at how far off I am. So that way this is no longer going to add up to 0. That can tell me how my residuals are like my errors. It's a way of looking at errors without values attached to them. And then for my component, what am I going to do? I'm going to take these numbers and put it over this. So in my calculator, I'm going to take my list 4, and I'm going to divide it by my expected, which is list 2. And so my components here are 1.53, 2.29, we'll just do it that way, 0.61, 1.11. Now, in all honesty, when I do this, I really only look at this guy. And so I want to do that with the least amount of work possible. So if this is my list 1, this is my list 2, and here I literally put list 1 minus list 2 squared over list 2. So watch what I do in my calculator. I arrow up to list 3. I say parenthesis, list 1 minus list 2 squared divided by list 2. And it gives me all those values. You guys okay with that? So those are your components. And that is now in my list 3. So what I'm going to do now is it says find, I've computed the components, now I'm going to find the sum of the components. Watch how nice this is. What I just did is I went second stat, because that'll give me all of my lists. I'm going to go over to math. You see 5 says sum. I'm going to do 5, list 3. So what I just did is I did sum of list 3, and it gave me 5.538. So far, so good. How many degrees of freedom do I have with this? 3. Because degrees of freedom is these numbers, which is 3. Now to test the hypothesis, I need to find, these are my mechanics here, I'm going to find the probability that chi-squared with 3 degrees of freedom is greater than, and that is always going to be greater than, that 5.538. That can be my p-value. Okay? Now, I just did the sum of list 3 in my calculator, right? Sum of list 3 is in my calculator. So now what I want to do, because it makes my life easier, I'm going to go to the store button, right down there, right above the on, and I'm going to store that answer as X, because I want to do as little memorization as possible, and I want to do as little rounding as possible. So I'm going to store that answer as X, and then to test the hypothesis, we're going to go to second vars, and guess what I'm going to use? Chi-squared CDF, because we don't use the PDFs. The lower number is always whatever your X was. The upper number is always going to be crazy 9s. Always. And so what I do is I plug this into my calculator once, then I don't need to change it for any of the other problems. The only thing I need to change is the degrees of freedom. There's my p-value. So the p-value is going to be 1.1364. Okay? What do I do now? Got my p-value. I need a conclusion. So I will say, with a p-value of 0.1364 being greater, what do you want to use for your alpha? Let's go with 0.05. Even if you were to use 0.1, it still would be greater than. We what? Do you reject or fail to reject? We fail to reject. And then what we say is we do or we don't. We do. So we have... No, we don't. We don't have. No, we don't. Stop listening, you people. Goodness, you're messing me up. I'm not even using my erasable pens. We don't have enough evidence to claim what? Right. There is a difference. And we're just going to state the rest of it. In the number of people who use each stall in public restrooms. What does that p-value represent? P-value says if what? If the null hypothesis was true. So if there really was no difference in bathroom stall usage, then then there's about a 13.6% chance of seeing a sample as extreme or more than ours just by natural sampling distribution. Now, or sampling variability. When I look at that, I think there's a 13.4% chance that there is no difference. Well, if there is no difference, there's a 13.7% chance of seeing our sample. I don't know about you. That's enough evidence for me to think. I mean, it might not be something I go out and put together advertisement and everything like that on, but I think that's enough for me so that I always try to remember this. And I look back at my residuals. If I look at my residual, which one had the least, the furthest from the expected on the most empty side? Had the fewest users. Stall 1 to me would probably be the cleanest, right? Furthest from the expected. Which stall would you avoid? I would avoid the second stall. And this really, to me, this is my choice pattern. I walk in the bathroom, I go to the first stall. If that's in use, I go to the last stall. Then I start playing around with the ones in the middle. Yay, coronavirus. Also, Mythbusters, really great video on why not to use the hand air blowers. They're basically just taking all of the stuff that's in the air and forcing it onto your hands. It's disgusting. So, this is a general way to do this. If we were to have come up with a conclusion that we rejected the null, we would have actually gone back, looked at our components, and talked about which component was the largest. That largest component would have been what the most unexpected results came from. And we're going to go and talk more about that also. Now, this is the long, drawn-out way to show your work. Okay, I'm going to do it next time where it's not quite so much work. Do you understand? This is a lot of work here, right? A lot of stuff to show. How can I get away with showing less? And to do that, we're going to look at this next question. Completely forgot. Yes. You're going to at least start it. Because I'm an idiot. Hi. Thank you. Get as far as you can. Stop when you're done. All right. So you see this is in your notes, right? This is a very, very common thing. We do this at the end of the year with the AP exam results. We look at the distribution of 5, 4, 3, 2, 1, and we look to see if they match our grades. It's a very important thing for us. And the biology professor claims that he gets about 15% A's, 30% B's, 40% C's, 10% D's, and 5% F's. So that's what his claim is. And then we actually have what the distribution was. So what I want you to do is we are going to go through and we're going to test the hypothesis. All right, so looking at this problem. Let's start with the null hypothesis. What would the null hypothesis here be? What would you say? You would say that and you can go as simple as the distribution. What are we measuring the distribution of? Of grades for this teacher, and you can say biology, I just am trying to be lazy. Of grades for this teacher. And for the null hypothesis, are we looking for does match or does not? Matches, so does match. And then you don't need to list out all of the things. You can just say does match her claimed distribution. What would be the alternative? Does not match. And then just the vertical quotes because that says bring it down, bring it down, bring it down. All right. So what next? My assumptions and conditions come next. What's my first assumption and condition? Counts. So in this case, the data are counts of grades. Not people here, but grades. How many of these grades did she give out? Okay? What comes next? Randomization. Do we have randomization? So what do we have to have? Hope it's representative. Because I would only be able to take these results to a group that kind of matches the general population of this group. So we're going to say we hope it's representative. Now, there's one more thing we need for chi-squared. What's that? Sample size. And for sample size for expected counts, what do we do? Greater than 5? All right, so let's go through and let's figure this out. How can I do this? Go to your stat, and please remember when you have things in your list, arrow up so that your list is highlighted and hit clear. If you hit delete, it will actually cut out that entire row. So if you see I hit delete and those rows are gone. So if you've accidentally done that, let's say you've deleted your rows like I just did. And by the way, guys, I will not help you with this on a test or quiz. You have to know how to do this yourself. If you accidentally deleted, go back to the stat button, setup editor, enter. Now when I go back to my list, they're back. And anything that was in there to begin with. So I'm going to, again, not delete. I'm going to clear those lists. And I'm going to, I'm going to put my observed. Yeah. And by the way, when you get these errors and it says gotta, that actually means go to. That goes to whatever your error was. My error was I put a plus sign there when I shouldn't have. So those are my expected counts. I'm sorry, those are my observed. My apologies. Now, if you'd like, you can add all those numbers up. Or you can go to your list and just take the sum of your list 1. That way I don't have to type them all in and add them up. So if I'm looking at this, I got that my total number was 325. Do y'all understand what I did there? If you don't want to do it that way, you really can just add those numbers up. I just prefer to hit fewer buttons. That's my thing. Lazy. Now you have a choice. For the expected cell count, you can either do, so if I go back to the distribution, here's my distribution, I can say 0.15 times 325. 0.3 times 325. 0.4 times 325. 0.1 times 325. 0.05 times 325. I can do it that way for my expected counts. If you want, you can also do 0.15, 0.3, 0.4, 0.1, 0.05, and then go back up and say list 2 times 325. So whichever way you want to do that. When you get those numbers, as soon as you get those numbers, write them down. So I'm going to write expected. So my expected cell counts here, I'm going to say 48.75, 97.5, 130, 32.5, and 16.25. So I literally wrote down my expected counts. So for my assumptions and conditions, what were my assumptions and conditions dealing with the expected counts? Greater than 5. So I can say all expected counts greater than or equal to 5. Now, my goal here is to show you what is the least amount of work that you need to show. All right, you ready for that? So what I'm going to say is I'm going to say my chi-squared. How many degrees of freedom am I going to be working with on this? 4, because I have 5 grades. Remember, n is not the number of people, it's the number of groups. Minus 1. 5 minus 1 is 4. So chi-squared is equal to. We're going to write the formula. For this guy, you need to write the formula so you can establish what you're doing. And I'm going to say sigma. What does sigma represent? The sum. I'm going to write observed minus expected squared over expected. If you want to do O minus E divided by E, that's fine. Now, when it comes to work for this, because we're going to have lots of tables, you don't want to write it out for every single one. You have to show it, and this is the AP grading rubrics, you have to show it for at least 2. 2 will establish a pattern. So that means I'm going to do observed minus expected squared over expected plus, I'm going to do it again for the next one, observed minus expected squared over expected. I'm going to do plus dot dot dot. Okay? In my calculator, to get the calculator to do that, I'm going to go over to list 3. I'm going to arrow up on list 3, and I'm going to say parenthesis, list 1 minus list 2 squared over list 2, because that is my observed minus expected squared over expected. So far, so good? And then I'm going to go to my second list and take the sum of list 3. So my chi-squared component is 62.538. And then I'm going to find what? After we found chi-squared, what did we do? How do we test the hypothesis? Probability of getting a chi-squared with 4 degrees of freedom that is greater than the 62.538. And so I'm going to store that number as my x. And I'm going to again do chi-squared CDF. Remember how I said we already have the x there. That's what's nice about storing it. I don't have to change that. The only thing I have to change is what? What do I need to change? Degrees of freedom is now 4. And so what do we get? We get approximately 0. Whenever you see that e, and that's e to the negative 13. That's like freaking crazy 0. That's teeny tiny. So what does that mean? We reject. So we're going to say with a p-value of approximately 0, that's going to be less than really any alpha, but I'll say alpha of 0.05. We reject the null. And what are we going to say? We have evidence, or enough evidence, to suggest, Suggest. How many G's in suggest? 2. Gosh. To suggest the claim does not match. And you would put all the words, but I'm running out of space here. Eden, don't worry. If you don't finish, you don't finish. It's okay. Right? You know what I'm talking about here? You okay that I don't write the whole thing out because I'm out of space? Which you might be also. You have the same paper. Look at what B says. B said, which grade impacted your decision the most? Go back and look at your lists. Which one of the chi-squared components is the largest? What number is the biggest here? The first one, right? That first component matches with what? Matches with what set of data? The A's. So since the chi-squared component on the A's is the highest, we would say which grade impacted the decision the most? The A's. So the grade impacted the most, why? If we were to compare observed minus expected, what would you say? Did you have more A's or less A's? What did you have? 89 and 48. What do you have? We have a lot more A's than expected. All right? Now, the one thing I didn't do on these problems that we're going to focus more on next time is going to be after your assumptions and conditions are met, you need to tell me what type of a test you're going to do. These guys have all been chi-squared goodness of fit tests. And this one had 4 degrees of freedom. So we are going to be putting that in, but that's because we're going to have more than one chi-squared test. The mechanics of it work all the same, though. Okay? There's 3 of them. All right. So, next class, you are going to have a test. Your AP Classroom has been opened up for your review. You have a My Math Lab that is not going to be due until March 18th. And when I say watch the video for Chapter 25, that doesn't need to be done until next week. Okay? That's going to be because your test is going to be on Friday. Video for Chapter 25 has to be watched before class on Tuesday. Study for the test, though. What else is going to be due next class? Flip books.